So this is number theory. So we're going to start looking at some primes. We're going to see some consequences of some of the stuff we've done before. We're going to talk a little bit more about how to count and how to ask some good questions. So the first thing is, what is a prime? I have not primed Kayla. What's a prime?
It's where it's only one in itself.
Only one and itself divide. Is she correct? Or is there a tweak that is something else you have to add? All right, someone help her out. Is your hand all the way over there?
No, but natural numbers?
Natural numbers.
It has to be greater than 1.
Has to be greater than 1. So we can say, another way of phrasing this is exactly 2 divisors.
No word, it was my answer.
Sorry? So exactly 2 divisors. 1 in itself. Composite is at least 3 divisors. And then if 1 divisor, it's the unit. Okay? So the first question is, how do we find primes quickly? Okay? And so one thing we talked about is we could try dividing every single number, but this is going to be time consuming. How many of you have seen the sieve of, I'm always going to misspell this, So how many of you have seen the sieve of Eratosthenes? This is a great way to generate all the primes up to a certain point. Now the problem is, from an implementation standpoint, this could require significant memory to store everything. We will ignore issues like that as a theorist. And so the way it works is the following, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'll do one more row. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, all the way to 100. Okay, so the last row would start off with 91, 92, 93, 94, 95, 96, 97, 98, 99. So the way the sieve of Eratosthenes works is you ignore 1, because 1's a unit. You take the first element in your table that is not marked. And so here we're going to do up to 100. I'm basically going to do an n by n table. So you circle it, and it's now considered prime. And now you throw away all multiples of 2. So I would throw away 4, 6, 8, 10. In fact, I throw away this whole column, this whole column, this whole column, this whole column, and this whole column. That's the advantage of writing it like this. Now I come to the next number. I haven't crossed out 3, so 3 must be prime. Because all the numbers smaller than 3, if they could have divided 3, I would have. So I now circle 3, and I declare 3 to be prime, and now I cross out all multiples of 3. You'll notice some numbers have already been crossed out that I would want to cross out. 6 is already gone, but now I would cancel 9, 12 is gone, 15, 18 is gone, 21, 24 is gone, 27, all the way coming down here. Anybody know the quick way to tell if a number is a multiple of 3? Yes. If the digits sum to a multiple of 3, the number is a multiple of 3. If the digits sum to a multiple of 9, the number is a multiple of 9. If the alternating sum of the digits is a multiple of 11, the number is a multiple of 11. If people are interested, we can prove these later. So 91 is not a multiple of 3, 92 is not, 93 is, we would cancel out 93, 96 is already canceled, we cancel out 99. We now come to 4. 4 is already canceled, so that means something went into 4. 4 is not a prime. What about 5? Prime or not prime? Prime. So now we circle 5, and what's nice is we can cancel all the multiples of 5. That's just going straight down. 6, already canceled, so 6 is composite. What about 7? Fine. So now we would cancel all multiples of 7. So we kill 14, 21, already got that. Next one is 28, already got that. You know, keep going. What's the first multiple of 7 we'll get? Well, okay, it's on this table.
77. Oh, on that table?
On this table.
91.
Yeah, 91. So we'd kill 91. 91 is often called the smallest composite that looks prime but isn't. Because the numbers that go into 91 are 7 and 13. And we don't have as much intuition with multiples of 7. So 91 kind of looks prime, but it's not. So there's a couple of other numbers left. So what's the next number on our list that's not crossed out? 11. Here's the interesting question. Could 11 divide anything on this list which is not crossed out? No, because remember, if a number is composite, if I can write n as x times y, either x is less equal to square root of n, or y is less equal to square root of n. So if I want to check all the numbers up to 100, to see if it's composite, I only have to check the numbers, the primes, up to square root of 100 or 10. So 11 cannot divide anything else. So anything that survives up to this point in the table is prime. So this is kind of nice. We only had to check multiples of 2, 3, 5, and 7 to generate the entire table of primes up to 100. Okay? So it's not clear from this whether or not there will be infinitely many primes. It's not clear at all about properties. It's not clear about spacings between them. The primes are our building blocks, so there's a lot we want to know about them. And we will get to some of these questions this year. I think there will be some analytic number theory classes next year which will get to these questions even further if you really love them. And some of your homework problems are actually related to stuff like this, where you will actually come up with some proofs. If there are any seniors who are looking for a good colloquium talk who haven't chosen one yet, a really nice one is 6 proofs of the infinitude of primes, or something like that. There's lots of different ways of showing that there are infinitely many primes. We will see a very strange one later today. I will have to assume a result, but actually I'll have to assume 2 results, but it allows me to introduce one of the most beautiful functions in all of mathematics. So I'm happy to do this. All right. I mentioned in the last class how annoying it can be to teach a class like number theory. Yes?
What was the condition that you said that for deciding if a number was divisible by 11?
Oh, so a number is divisible by 11. So 11 divides, and I don't want to write a slash because 1, 1 slash would just be a horrible thing to write. If the alternating sum of digits is 0.
Does that generalize to other bases?
It does. Now, this is where I love the fact that this is a small class. If you guys want to see these divisibility rules, I'm not wedded to the curriculum and when we do things. I'm happy to do them right now. Who wants to see these? Do you want to see them, Kayla? Okay. She has veto power over me, so let's go these. Now, ideally, you would have taken a class called abstract algebra. It is possible to be a somewhat successful mathematician and never take a class like abstract algebra, but I highly recommend you do that, and that will give you a good framework for stuff like this. So I'm going to do divisibility by 3 and 9. So n is a multiple of 3, respectively 9, if sum of digits is a multiple of 3, respectively 9. Proof. I can write 10 as 9 plus 1, and 9 is a multiple of 3. I can write 100 as 99 plus 1. Is 99 a multiple of 3? Is it a multiple of 9? Yeah. I could write 1,000 as 999 plus 1. All these numbers here are multiples of 3 and 9. So now imagine n, it's, d, I'm going to do it with a specific number, and then I will leave you the notation of just writing it out in full generic form. So let's say n is 24601. Can anybody tell me why I chose that number?
Is that minus 1 is divisible by 3?
She said minus 1 is divided by 3. Nope. Right, nobody know why I chose 24601? Les Mis. Jean Valjean. Right? I really identify with Cosette because I worked in restaurants for many years for equivalents of innkeepers. I like Jean Valjean. Okay? Let's check and see if this number. So this is equal to 2 times 10 to the 4th plus 4 times 10 cubed plus 6 times 10 squared plus 0 times 10 plus 1 times 10 to the 0. And so now if you look at what's going on, this is equal to 29999 plus 1 plus 4999 plus 1 plus 699 plus 1 plus 0, 9 plus 1 plus 1, 0 plus 1. And so if you look at what's going on, we have 2 times 9999 plus 4 times 999 plus 6 times 99. And this is clearly going to be a multiple of 3 and 9. And then what's left over? 2 times 1, 4 times 1, 6 times 1, 0 times 1, 1 times 1. 2, 4, 6, 0, 1. So now, if this number is a multiple of 3, since this is a multiple of 3, the sum must be a multiple of 3. If the sum is a multiple of 3, since this is a multiple of 3, then the original number must be a multiple of 3. And the same holds for 9. So I really don't want to write this digits as D0, D1, D2, D3, all the way up to DL, but that's all you would do for the general proof. Yes?
So if we were to write our claim more generally, could we say n is a multiple of like b minus 1 if the sum of its digits in base b is a multiple of b minus 1?
So you've got to be careful sometimes as to, does something involve special properties of 10? So over here, 100, I can now write as 9 times 11. I can write 1,000. So the question we want to know is, can I always write b minus 1? I'm sorry. Can I write 10 to the m? Sorry, we're doing it base b. Can I write b to the m as a multiple of b minus 1? Sorry. Plus 1. Yes.
Would be b plus 1 times b minus 1. Oh wait, sorry, not b. You for like b equals 2, you can do it, and I think I know you can do it for each one.
So one of the things is we can write 10 as 9 plus 1, and then when we expand things out, when we use the binomial thing, we're going to keep getting 9, 9, 9, 9, 9, 9, 9, 9, 9. So if we want to write, we can write b. We can write b as b minus 1 plus 1. Raise it to the nth power. This is then going to be b minus 1 plus 1 to the nth power. And now when I expand everything that has a b minus 1, I don't care what binomial coefficient hits it. It's going to be a multiple of b minus 1. And I'll be left with a plus 1 at the end. So your claim is correct. So that this test would always work for 1 less than the base. For 11, n is a multiple of 11 if the alternating sum of the digits is a multiple of 11. And the proof here is a little bit harder. So how do I want to write 10 in terms of 11?
11 minus 1.
So 10 is 11 minus 1. So 10 squared is 11 minus 1 squared. And when you expand this out with the binomial thing, I only care about the part that's not a multiple of 11. I'll get 11 squared minus twice 11 times 1 plus 1 squared. So this is basically going to be equal to a multiple of 11 plus 1. So how many of you have seen clock arithmetic or mod arithmetic? This is something we were going to do later in the semester, so we're just jumping ahead to chapter 2. So it's so useful, it's worth doing now, and in this way we'll have better language. Okay, it is approximately 10 o'clock right now. What time will it, let's say it's 10 o'clock exactly. What time will it be in 5 hours?
3 o'clock.
Kayla? Okay, you agree?
PM.
PM. Oh. So what you're just saying is 10 plus 5 equals 3. Is this what you're saying, Kayla?
An hour? Yes, but not. But if it was just numbers, it would be 15.
So it was just numbers would be 15. So what's different about hours? Yes.
Hours only go up to 12.
So what happens once you get past 12?
It starts at 1.
It starts at 1. So we reset. Now, as a mathematician, would we really want to have numbers from 1 to 12? What would we want to do? I see you shaking your head. What would we?
Any would be better.
Well, no. We can deal with.
We're just used to it.
We don't want 1 to 12. How should we do it?
0 to 11.
0 through 11. Right? So there's the joke of a very absent-minded mathematician, Norman Wiener. And he's moving, and his wife tells him, watch suitcases while I go inside and check some stuff in the house. There should be 10 suitcases. And when she comes back, he says, I don't know what happened. We're missing a suitcase. What do you mean? We only have 9. What? Look. 0, 1, 2. The other absent-minded story they tell about him is that he forgot that they moved, and he comes back to his house, and he realizes that they've moved, and he forgets where they moved. But fortunately, he sees a little girl playing in the street, and he goes up to her and says, excuse me, my name is Professor Wiener. I used to live in this house. Do you happen to know where I have moved? And the little girl says, yes, Daddy. Mommy thought you'd forget. Now, there are other versions of the story where he at least recognizes that it was his daughter. But his absent-mindedness was somewhat famous. We love to start counting with 0. We don't want to start counting with 1 and have 12 and reset. So the clock arithmetic, modulus 12, means that n is congruent to m mod 12 if n minus m is a multiple of 12. And so we use the triple equal sign to indicate congruence or equivalence. So we're not saying that the numbers 15 and 3 are the same, but we're saying for all practical purposes, for what we care about for this problem, they have all the properties that matter. All that matters is their remainder when we divide by 12. And fortunately, we did do the division algorithm last week. Okay. Sometimes people might put a subscript 12 down here rather than writing the mod 12 over there to just tell you what the modulus is. For humanity, what do you think the most important modulus is? 10? Not really 10. Not 2.
I'd say 1.
So sometimes it's 1 in terms of just looking at fractional parts of numbers. Sometimes it is 2 if you're doing things in computer science. Is it on or off? What else for most humans, though? Probably 12 for most people. Now, the computers in the background that are making our lives pleasant, those are going to be base 12.
Is it 12 just for the hours?
Yeah.
Oh.
I mean, if you think about where most people use modular arithmetic or clock arithmetic, not surprisingly, it's with a clock.
And the rest of the world is 24 then.
Yeah.
For a lot of, yeah, we don't really care about it. All right, so for the rest of the world, it's 24. 24 or 12. Okay? Okay, you gotta do a little 5. So for the rest of the world, it's 24. For us, it's 12. That's what we're using for clocks. For some of the stuff in terms of looking at properties of numbers, sometimes only the fractional part matters. And you would look at things mod 1. And so two numbers would be the same mod 1 if they have the same fractional part, the same decimal expansion. So when we're doing all this stuff over here, a much better way of saying this is, 10 is equal to 11 minus 1. So this is going to be congruent to minus 1 mod 11. This, which is a multiple of 1, I can now say this is equivalent to 1 mod 11. What about 10 cubed? What will that be?
This one.
Yeah, 11 minus 1 cubed. So the only thing that's going to survive now is the negative 1 cubed. This will be minus 1 mod 11. And the next one, 10 to the 4th, would be 11 minus 1 to the 4th. Now you'll get negative 1 to the 4th. Now you'll get 1 mod 11. So what you can see now is you're going to get this alternating sum. And it doesn't really matter if you start with a plus 1 or minus 1. As long as you alternate, your alternating sum will either be correct or off by a minus sign. That's not going to affect divisibility. So this is a really fast way to tell if your number is a multiple of 11. How do you tell if a number is a multiple of 2? I'm sorry?
Just check the last digit.
Yeah, check the last digit. Is the last digit a 2, 4, 6, 8, or 0? Multiple of 4. Last two digits. Because 100 is a multiple of 4. Multiple of 8, check last 3 digits because 1,000 is a multiple. 5 is the last digit is 0 or 5. So the only one that's a pain is 7. There is a rule for 7, but the rule is worse than just actually, it's almost worse than doing the division.
What
Is it?
Well, what you would do is you would look at what is 7, you would write 10 is equal to 7 plus 3. So 10 is equivalent to 3 mod 7. 100 would be equivalent to 3 squared, which is 2 mod 7. So you would have this weighted sum. Yes?
I actually know a different way of doing it.
Oh, good.
If you write out like a number,
Right?
and you use the fact that 21 is divisible by 7 and subtract basically 21 times the last digit off the number.
Okay.
So, can I?
Sure.
I mean, it's still not great, but like it's
Right.
better. It's better than like that nonsense. So like, let's say you have like what number should I use?
24601. Oh, that'll make it big as well. 241. 246.
246. Okay.
Yep.
So what you do is you'd because 21 is divisible by 7, you can just take 2 times 6 and get rid of the 6 and go 2 times 6 is 12, and then 12, and then 12 isn't divisible by 7, so it's not. This isn't divisible by 7. It might be better if I had more things, but
Right.
because basically what you're doing is you're saying you're at this. Basically what you're doing is you're taking 246 and you're subtracting 21 times 6.
Right.
And then because 21 is divisible by 7, you know this, and so 6 just gets canceled out.
Right. What you're doing is you're basically trying to throw away a big chunk of the number and reduce it to something smaller.
Yeah.
And then the question becomes, how much do you save? They taught my son a strange way of multiplying numbers by doing powers of 2 and grouping things. I'm debating whether or not to go into their class and tell them why it works. We might do that later this semester. But there are these nice divisibility rules. Some things are nicer than others.
I mean, I would normally just divide it out, but
So it's a question
also
of,
because this doesn't tell you, it doesn't tell you mods or the remainder very easily.
right. So the question is, what information do you need to know? And sometimes you just need to know, is it a multiple? So we'll eventually get to Fermat's little theorem, which you just need a number that's relatively prime to a certain thing. And that we don't need necessarily the remainder.
7 shouldn't be an integer.
No. We have 7 days in a week, 7 points for a touchdown followed by an extra point. We got to keep 7s. Otherwise, we have to watch 2-point conversions every single time. So let's go back to what I was going to do, but I don't mind. I love digressions like this. This is the class where we can have stuff like this. We're going back to how painful this class can be and boring, so please do things like this so it can be fun. You can spend all of your time proving the blatantly obvious and getting frustrated. So one of the things we need to prove is if a prime divides a product, must it divide at least one of the terms? And then the question is, what is your definition of prime? So here is a nice one. Does sine of x divide cosine of x? Does sine of x go evenly into cosine of x? We agreed no, correct? What about 1 minus cosine squared of x? Does sine go into that? Yeah. We can write this as 1 is sine squared minus cosine squared. So this is actually just sine squared x. So you can get into strange situations. Now, we could factor this as 1 minus cosine of x times 1 minus sine of x equal, 1 minus cosine of x, 1 plus cosine of x. Right. I've just factored 1 minus cosine squared. And this is now sine of x times sine of x. Sine of x clearly goes into the right-hand side. I'm being extremely cavalier. I can do this, I'm a professor. Sine of x goes to the right-hand side. Does sine of x divide either 1 minus cosine or 1 plus cosine? No. So this generalization of, what does it mean to be a primitive element? We've got to really think about this when we try to generalize from numbers, from integers, to higher groups. There's other examples you can do involving square roots, like 1 minus root 5. I'll just quickly say this. If I give you 1 minus the square root of negative 5 and 1 plus the square root of negative 5, what does that equal? Not 8. It's negative 4.
6.
6. I get 1 squared, the cross terms cancel, and square root of negative 5 times square root of negative 5 is negative 5, and there's a minus sign, so it's 1 plus 5 is 6. And 6 is 2 times 3. Does 2 divide 1 minus square root of negative 5? Does 2 divide 1 plus square? No. So you can have these strange situations where these elements can't be decomposed, but they don't always divide what's on the other side. And so the numbers really have special properties. This unique factorization, this a prime divides a product implies a prime divides at least one of the terms. This is big news. This is not something small. This is not something you always have. We are extremely fortunate that this is true. And we love generalizations of the numbers that have this property. So what I want to do is I want to quickly prove this result. So theorem. Well, I'll make it a theorem. I'm going to generous proof today. If a prime P divides AB, then P divides A or P divides B. Is it possible P could divide both A and B? Yeah. Give me an example where P divides A times B and it divides each one.
P is 2 and A is 4 and B is 6.
Yeah. There's lots of examples. There's the difference between the inclusive OR and the exclusive OR. This is just telling us at least one of the two must be true. It's not telling us exactly one of the two is true. All right. So the proof. Case 1, P divides A. All right. Given that P divides A, I have to show either P divides A or P divides B. This case is not so bad. So, case 2, P does not divide A. So what does it mean if the prime doesn't divide A? This implies the greatest common divisor of P and A is what?
1.
Is 1. Because the only numbers that divide P are 1 in itself, right? So the greatest common divisor has to be 1. By the Euclidean algorithm, there exists, say, alpha and beta, such that alpha A plus beta P equals the GCD, which is 1. Right? So we're now going to begin to see why the Euclidean algorithm is so good, and why Professor Adams was at such a handicap when he had to argue against it. Right? What should I multiply both sides by? B. We're trying, excellent. We're trying to show P divides AB. I've got an A over here. It's screaming that it wants a B. So we now multiply by B, and we get alpha AB plus beta PB equals B. P divides. You do not want me to show that if a prime divides two sums, summons, it divides their sum. You do not want me to do this. If you think you want me to do this, you are mistaken. Okay? So we will accept that. Okay? So P divides the left-hand side, therefore P must divide the right-hand side. So therefore P divides P. And so now we have, if a prime divides a product, it has to divide at least one of the two terms. This is a great result. Okay? So now we can use this and we can move into unique factorization. So this is the fundamental theorem of arithmetic. And again, you do not get the designation fundamental lightly. This is a big deal. I think we talked earlier in the semester about how many fundamental theorems do we know, and the list is short. So the claim is any n greater than or equal to 2 can be written uniquely as a product of primes in non-decreasing order. So I can write n as p1 to the r1, p2 to the r2, dot dot dot, pn to the rn, where pi is less than pj if I is less than j. So if I didn't force the primes to be, in non-decreasing order, I could just reorder the factors, and it's not really interesting. I don't want to consider 2 times 3 times 2 different than 2 times 2 times 3. Okay? And we can see now why we do not want 1 to be a prime. If 1 is a prime, it screws up this theorem. We no longer have unique decomposition. Because 1 is a unit, I can't use it in the decomposition. Okay? So we want to prove this result. So there's lots of different ways of proving this. Probably not too surprisingly, we're going to use stuff that we've already been doing this semester. And technically we are now in week 3, so we're now somewhat deep into the semester. Okay, proof. Let's go by induction. Okay? What do you want to do by induction? Nah, we always do things by induction. Let's do a different proof. Let's go proof by well ordering. By well ordering, if false, what must be true? I'm just bored with induction. Gotta break the habit. What must be true by well ordering? So if our claim is false, if the fundamental theorem of arithmetic does not hold, your life is no longer good, and what must be true?
There's 2 ways to write it as factor primes.
Well, there's a number that has 2 ways to write it. What else do we know about the set of exceptions to the fundamental theorem of arithmetic?
This is the smallest one.
There's the smallest one. The well-ordering principle tells us of any set of positive integers, there is a smallest. Let n be the smallest failure, which exists by the well-ordering principle. There must be a first element that fails. We know n is greater than 2 because we know 2 can be written uniquely as a product of primes. So we know n is greater than 2. So assume we have a failure. So then we can write n as p1 to the r1, pn to the rn, and we can write this also as q1 to the, I guess I should do s1, I hate using s, but qm to the sm. Okay? So these can't be the same factorization. So they must differ. There must be a prime that divides the left-hand side that doesn't divide the right-hand side, or a power of that prime that doesn't divide So for instance, maybe they're both multiples of 2, but this is a higher multiple of 2. Okay? Let's just do the simple case where well, here, what we can do is, if there are common numbers on both sides, we could remove them. If 2 cubed divided the left and 2 to the 4th divided the right, we could remove 2 cubed from both sides, right? And that wouldn't be the smallest. So without loss of generality, these primes have to be different than those primes. Because if they weren't, we could just remove the smaller power. Is everybody comfortable with that? So without loss of generality, primes on the two sides are distinct. Because if a prime divided, if your P1 divided this side and this side, I can remove P1 from it once. And I would then have a smaller number, which would be a contradiction. So P1 divides the left, but it doesn't divide the right. So P1 divides left-hand side, but it's not a Q1 through Qm. What's the contradiction? What we just proved. So can we immediately use what we just proved to say contradiction? If a prime divides a product, it has to divide at least one of the terms. Did we prove that? I know, you're giving me this look.
Is it because like there's several?
Yes.
Too?
And this is why people can hate me.
But can we like make them like
Yes.
several too?
So what we need to do is we need to go back in time and say, crap, we didn't write the statement well. It should be if P divides a product A1 through AN, then P divides either A1 or A2 or A3. So we just have to finish the proof by grouping. Okay? It's not that bad, but you have to just do it. So what you could do now is we've got P1 divides Q1 to the R1, Qm to the Rm. So we can say either P1 divides Q1 to the R1, or P1 divides Q2 to the R2, Qm to the Rm. And then technically for this one, we would have to write P1 divides Q1, 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 all those odd times. So you just basically say, go back in time and fix previous result. And so what we would now do is if P divides A1, A2, Am, we know P divides A1 or P divides A2 through Am by just grouping them. And then by induction, this is now a product with one fewer term, and we're now done. So I strongly urge you to write this all down very carefully. This is what's really going on. It's not that bad because things are finite. If we had infinite series, this would be very different. So the derivative of a finite sum is the sum of the derivatives. You normally only prove the derivative of f plus g is f prime plus g prime. If you wanted to then prove 3 terms, if you have f plus g plus h, and you want to take the derivative of that, what you do is you first group f and g together. And then this would be f plus g prime plus h prime. And then this is f prime plus g prime plus h prime. And then we drop the parentheses, and we have f prime plus g prime plus h prime. And you really just argue like this. And as long as it's a finite process, you're fine. But if you have an infinite process, it can fail. The derivative of an infinite sum is not always the infinite sum of the derivatives. You have to be very careful whenever there's an infinity. Everything here is finite. This is no problem. Are we all comfortable now that unique factorization exists? That if there had been an exception, we could have found a smaller exception. Okay, just whenever I go that far off, you can press trouble. Okay. So we're now comfortable with all this. Why do we care about unique factorization? Okay. I know Cameron knows the answer to this question. I don't know if Taylor knows this one. Somebody give me the smallest prime greater than or equal to 2017. What's the smallest prime greater than or equal to 2017?
Is it 2017?
Yeah, it's 2017. 2017 is prime. What's the next prime after 2017? I'm waiting. All right, fine. I'll ask an easier question. What's the next? Caleb, this will be for you. You missed the class. You ready? What's the next number after 2017?
2019.
Next one.
2019.
Keep going.
2020.
Keep going.
2021.
She's a machine. There's really no mystery in this distribution of the integers. Right? If I tell you an integer and I ask you, what is the next integer? You know, it's nice that we have a ringer from second grade here. We really don't need to know that much. There is no mystery. But the primes, very deep how they're distributed. The whole idea of a lot of analytic number theory is we introduce a special function called the Riemann zeta function, which allows us to pass from knowledge of integers to knowledge of the primes. And because the integers are extremely well understood, we did not rehearse this. We can pass from knowledge of the integers to knowledge of the primes. So the Riemann zeta function. So zeta, the Greek zeta of S. We define zeta of S to be the sum, n goes from 1 to infinity, of 1 over n to the S. And this is true for the real part of S greater than 1. I'm allowing S to be complex. If you're uncomfortable with that, you can keep S to be real for now. If you want to go deep in number theory, you really want S to be complex. But a lot of the applications, S real is fine. You might remember your P series from calculus. You know, when does the sum of 1 over n to the P converge? This converges if P is greater than 1, and it diverges if P is less than equal to 1. You might remember this from your calculus classes. It's horrible notation if you continue to number theory because we want to reserve P for primes. Okay? So you've seen hopefully P series before. You've hopefully seen that this converges. It turns out, and this is why we love this so much, this is also the product over all primes, P is a prime, of 1 minus 1 over P to the S inverse. And because the way you write things is often important, I will write this as a product over P prime of 1 over 1 minus 1 over P to the S. Does this look like anything you've seen before? What does this look like? Geometric series. Okay? And we talked about the geometric series earlier. So the idea, and I'm only going to sketch the proof, is the following. 1 over 1 minus x is 1 plus x squared plus x cubed plus double double dot. Geometric series. So if I look at 1 over 1 minus 1 over P to the S, this is 1 plus 1 over P to the S plus 1 over P to the 2S plus 1 over P to the 3S. Dot, dot, dot. So if I look at the product of all primes of 1 over 1 minus P to the S inverse, this is going to be 1 plus 1 over 2 to the S plus 1 over 2 to the 2S plus 1 over 2 to the 3S plus dot, 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 times 1 plus 1 over 3 to the S plus 1 over 3 to the 2S plus dot, 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 dot. I'm not going to go through all the details now as to how you make this rigorous and how you converge. If you are interested, let me know. I'm happy to go into this. I just want to give you the broad brushstrokes. When I multiply everything out, the way we deal with an infinite product is you can only have finitely many terms that aren't 1. Another way you could look at it is, if I have this infinite product, I take the product only over a finite set of primes, and then I let that set grow. So when I multiply everything out, I will get things of the form 1 over 2 to a power times 1 over 3 to a power times 1 over 5 to a power. By unique factorization, that's the same as my number 1 over n to the s. And so what you show is that everything in here is here, and everything in here is here. These two are the same. And because they're the same, they're equal. Okay? You have to do a little bit of work on convergence, but this is just the broad brushstrokes. Okay? So the reason we care about this is the integers are very well known. Let's use properties of the integers to get properties of the primes. So what I will do is I will give you two quick proofs that there are infinitely many primes by looking at this function at special values of s. There's one choice of s that you may have seen before. What? Yes.
S equals 2.
There's s equals 2, but I think it's a simpler one. One. So if we take s equals 1, it's the harmonic series. Okay? So if s equals 1, it's the harmonic series. And what do we know about the sum of 1 over n? It goes to infinity. If there were only finitely many primes, what would happen if you put in s equals 1? It would be finite. So if there were only finitely many primes, this would be finite as s goes to 1, but this blows up. What can you conclude? What can we conclude? Infinitely many primes. And in fact, if you know that the harmonic series diverges like log x, so if you know that the sum of 1 over n less equal to x is equal to log x, let me just give you a quick heuristic. All right? I would use strong language, but my daughter's in the room right now. So let's say we know this, we remember this. And I'll put an approximate. So let's say the sum of 1 over n less equal to x is approximately the product of primes less equal to x of 1 minus 1 over p. Not quite right, but let's say it's approximately true. Whenever you see a product, what do you want to do? I've got at least 3 students who've seen me do this before. When you see a product, what do you want to do? Take the log. The log of a product is the sum of the logs. So now if we take the logs, this over here is about log x. So when you take logs, you get log x is approximately the sum p less equal to x, and there's a negative 1, of negative log 1 minus 1 over p. Well, the log of 1 minus x is approximately negative x when x is small. It's using Taylor series. So this is approximately the negatives reinforced. The sum p less than equal to x of 1 over p. And it turns out you can make all of this rigorous. And the sum of the reciprocals of the primes up to x is really about log x. So not only are the primes diverging, but they're diverging so rapidly that the sum of the reciprocals blows up. This is much better than what we got with Euclid. Euclid had, if you go up to like 2 to the 2 to the n, you would see at least n primes. That's going to converge greatly. There's going to be fewer primes according to Euclid's bound, and there would be perfect squares. So this is one power of the Riemann zeta function. Just really quick calculation, and you can make this rigorous. There are infinitely many primes, so much so that the sum of the reciprocals diverge. But even if you don't want to go into that, just looking at s equals 1, and the fact that it's the harmonic series, that's already enough to get the infinitude of primes. The next one, if s equals 2, it turns out zeta of 2, which is the sum of 1 over n squared, it turns out this equals pi squared over 6. What kind of number is pi squared?
Irrational.
It's irrational. This is irrational. Well, if this is irrational, if there were only finitely many rational numbers, what can you tell me about a finite product of rationals? It's rational. Because pi squared is irrational, there must be infinitely many primes. So this is an extremely strange proof. At first glance, it gives you no estimate as to how quickly the primes grow. It just tells you if there's not infinitely many, something bad happens. So years ago, with a couple of students, I decided to see, could we get an estimate as to how fast the primes grow? And I actually got an estimate out of it. Unfortunately, I didn't realize at the time that I was using a result whose proof used the prime number theorem. So by using the prime number theorem, which says the number of primes up to x is about x over log x, I was able to prove a weaker lower bound, which is not that impressive. So since then, I've actually gone through and I've opened up the proof, and I've removed the result that needed to use the prime number theorem. My result is now a little bit weaker, but my students and I were able to get very close to the prime number theorem by using known facts about how irrational pi squared is. So there is a way to talk about which number is more irrational than others. And I will end with the last comment. What is the most irrational number in the universe? Any thoughts? Phi, the golden mean. The golden mean is the most irrational of all irrationals. And if this is something you want to find out why, we can definitely do that this semester. So I'm trying to just give you some sense of where things go. I grabbed Bunchkins, but not the Munchkin on the way out.